In the previous video, we introduced kind of the basic properties of exponential functions with the general base and logarithmic functions with the general base. In this video, we are going to concentrate in on the more calculus-related properties, i.e. the associated differentiation and integration formulas. So if I'd like to differentiate a to the x, which I would like to do, what I can do is rewrite it as we've defined it previously. So that would be the derivative of e to the x ln of a. And we differentiate this with the chain rule. So we think derivative of the outside evaluated at the inside multiplied by the derivative of that inside function. Our inside function is x natural log of a. And remember, natural log of a is just a constant. So the derivative of x times a constant is simply the natural log of a. That is, the derivative of a to the x is equal to e to the x natural log of a, which is a to the x, multiplied by ln of a. So ln of a times a to the x. Now, note in terms of the exponential function we already know how to differentiate e to the x, this makes perfect sense. Because natural log of e is 1, this is the derivative of e to the x is equal to natural log e to the x, which is e to the x. So just noting, check, this makes sense compared to our previous use of the formula. Now, restating this in terms of an anti-differentiation formula, the antiderivative of a to the x is going to be 1 over the natural log of a to the x plus c. So two very important formulas related to differentiation and integrating of general exponential functions. Now we would also like a formula for the derivative of the log base a of x. And this is something we mentioned previously, just a bit of foreshadowing. But let's go ahead and work through the details again. The derivative of log base a of x, if we rewrite this with the change of base formula, this would be the derivative of the natural log of x divided by the natural log of a. And the nice thing here is, once again, remember, natural log a is a constant, so we can think of really as having 1 over the natural log of a multiplied by the derivative of natural log of x. So that would be 1 over the natural log of a times the derivative of the natural log x. So 1 over the natural log of a multiplied by 1 over x. So let's now look at a few examples involving differentiation. So let's begin by differentiating x to the x. Now this is something we've not previously encountered, and what we want to do is use kind of properties that we've seen. So what I'm going to do is note that there's really two methods. The first method is you could use logarithmic differentiation. Or you could just rewrite using the inverse properties of the exponential and natural log function, which is what I'm going to do. So I'm going to rewrite this as e to the natural log of x to the x. And recall, a power inside the natural log can be pulled out front as a constant. So this is really e to the x natural log x. So now all of a sudden this is a very reasonable function for us to differentiate. So dy dx is going to be the derivative of e to the x ln of x. So by the chain rule, this would be the derivative of the outside evaluated at the inside times the derivative of the inside. Now this e to the x ln of x, if we trace our work backwards, that's really just an equivalent way of writing x to the x. And when we differentiate x times the natural log of x, we'll use a product rule. So the derivative of the first times the second plus the first times the derivative of the second. And just to simplify this slightly, this is really x to the x multiplied by the natural log of x plus 1. Now, let me kind of note for you, and I'll leave a few details for you, that you could also do this or evaluate this with logarithmic differentiation. So when you have y equals x to the x, you can take the natural log of both sides. Natural log y is going to equal x natural log x. And now proceed as we've done previously. Implicitly differentiate both sides with respect to x, and then solve for y prime. And when you do, you will get, hopefully, the exact same formula that we have above. So another example for us to practice, let's find the derivative of x times 6 to the 2x. So as a reminder, our new formula involving differentiating general exponentials, the derivative of a to the x is natural log a to the x. Now, something else worth mentioning is that we can certainly combine this with the chain rule. If you have a to the u of x, you'd say the derivative of the outside function evaluated at the inside function times the derivative of the inside function. But we don't necessarily want to use that property if we don't have to. And what I mean by that is just using properties of exponentials. 6 to the 2x could be written as 6 squared to the x, because when you raise an exponent to another exponent, you multiply them together. So this would be x times 36 to the x. So remember, sometimes a little bit of algebra can definitely go a long way. So using the product rule, we take the derivative of the first times the second plus the first times the derivative of the second. And when we differentiate 36 to the x, we use our formula above. Each a becomes a 36. So natural log 36 times 36 to the x. For our next example, we have one of these compositions that we just mentioned. We have 5 raised to the power sine of x. And to differentiate something like a to a function, we differentiate the outside function, ln of a raised to a power. We evaluate at the inside function, multiply by its derivative. So even though this appears maybe to be a difficult example at first, it should work out quite efficiently. So 5 raised to sine of x. So we differentiate the outside function, ln of 5 times 5 raised to that power. We evaluate at the inside function sine, and we multiply by the derivative of that inside function sine. Then the derivative of sine is cosine. So we very quickly come up with the desired differentiation formula. One last derivative involving exponentials, the derivative of x squared plus 1 raised to the sine of x. Now this is very similar to that first example that we encountered. Now note that our function that we're differentiating is really something of the form f of x raised to a function g of x. And when we differentiate something of this form, what we would like to do is rewrite it using properties of exponentials and natural logs. This becomes e to the natural log of that, which would be e to the g of x natural log of f of x. And when you rewrite in this form, you can differentiate using just the chain rule. So rewriting y is equal to e to the sine x multiplied by the natural log of x squared plus 1. And once we rewrite it, we can hopefully very quickly, or at least efficiently, differentiate. Say it's a chain rule problem, so you take the derivative of the outside, evaluate it at the inside, and then you multiply it by the derivative of the inside function. Now this e to the sine x ln of x squared plus 1 note is exactly the function we started with. So you don't have to rewrite it, but I typically do. I would write this as x squared plus 1 to the sine of x, so it's that original function. And then we differentiate what's above using the product rule. So the derivative of the first times the second plus the first times the derivative of the second. To differentiate natural log of x squared plus 1, that's a chain rule problem. So you take the derivative of the outside function, 1 over, evaluate it at the inside function, x squared plus 1, and then you multiply by the derivative of the inside function.